Right, so welcome to the 11th, is it? Yes, lecture on random processes. Um, we have already done some recap, but I'll quickly mention what did we do last time. It was about covariance, right? So we have been working with the moments, remember? First moment, mean. Yes, we've already discussed that several times. Second moment, for single variable, variance, degree of spread, right? Now the third moment, within the second moment, when we go from one to two variables, we got the concept of covariance, remember? And we actually wrote a formula that led us to this covariance formula, which was, we ended up saying that, let's say if we had Vax plus By, where a and x and y were random variables, a and b were some constants, non-random variable. We ended up finding, I'm not going to solve it again, but we did this, right? And we resulted or found something new here, that was E of x minus mean of x times y minus mu y. We gave that measure a name, yeah, and that was cov xy. Yes, so this is also second order moment, but for two random variables. And last time we did very thoroughly discuss various aspects of the covariance, right? Can you recall any aspect that we discussed for covariance? Firstly, what is, in a just a few words, what is the meaning of covariance for us? Like variance, degree of spread, yes,
Statistical relation.
degree of linear dependence, statistical dependent, yeah.
One variable is increasing, the another is also increasing.
Increasing, yeah. So the increasing away basically above its mean, or decreasing below its mean. So the reference for each one is their mean, yeah. So the degree of statistical linear relation,
yes.
That was it. And we said, as we have already mentioned, if you plot x and y, if you do this thing like this is
Positive
highly
correlation.
this is high covariance, yes. And if the spread is like this is high negative covariance. But if they become like all spread out, or a circle, or something else, then at least this measure doesn't work that way, yeah. However, we can still use this measure if we can find there is some sort of seasonal behavior going on, right? So we can model the seasoning separately, and then what's left, that we try to see, is there now some sort of covariance between them or not, yeah. When we come to ARMA modeling and those things, there we will see this. And finding these seasons and those things, trends, that's in another course. Time series analysis, nonlinear time series analysis, that's a separate course. Here I will give you some hints of that by the end, but we won't go into all of that, because of course you have to limit the material, so much to learn. But just be sure that it's not like as soon as the relation is nonlinear, the whole concept of covariance becomes useless. Is that the answer? No. Okay. Always have this in your mind. Always ask. If you are learning, if you are teaching, a student may ask you, okay, you are saying it works only for linear relations, but if there are nonlinear relations, what do? We still mostly use covariance, but with some additional modeling involved. Okay. So degree of linear statistical relation. That means it won't cover nonlinearity. Okay, that was the concept of it. Yeah. Another thing is that well, I'll let you recall. What did we say about, let's say, the relation or between between dependence, having covariance or correlation, and independence. So correlated versus independent or dependent. What was the relation?
And dependence, it implies uncorrelation. And
So independence,
yes, sir.
if two random variables are independent, it definitely implies that they are
Uncorrelated.
uncorrelated. related. But if we say they are, if we say they are uncorrelated,
It doesn't imply.
it does not necessarily imply that they are independent. What does that mean really for us practically? See, if you have worked with the very basics of the random variable, for example, you have shown in terms of, let's say, probability A, remember that thing, A and B equals PA times PB, if you have shown this, or how did we say in PDF, right? It was the joint probability of, let's say, two random variables A, B, if it was their product of their individual probabilities. Remember, these were different tests of independence. If you have shown it like this, then you can, if you proved the independence like this, then you can assume uncorrelated will definitely hold. Okay, but if you have only shown that they are uncorrelated, how have you shown that? Let's say you found the covariance of two random variables. Yeah, you found it to be cov x, y, and it turned out to be 0. You calculated, you found it to be 0. Always remember, don't make a claim bigger than its actual level. That's for politicians, right? Your claim jitna hai, keep it there. Yes, don't try to run bullet trains in Pakistan. There's no need. What will we do? Go to Multan, eat nihari or something, right? So, if you find the covariance of x, y to be 0, the most you should say is that they are uncorrelated. Okay, you cannot claim that they are independent, because this holding will not imply this holding, but this holding will definitely imply this holding. Why? Remember, this led to another thing, that EXY, if XY were independent, EX and EY were separable. Yeah. Now within its definition, it contains that thing, that this is EX minus mu x times y minus mu y. If they are independent, then by necessity of this, you will end up taking mean of separately.
Yes.
But then it's x minus the mean, that both factors will be 0. Yeah. So if you find this, yes. Now either you find like this, that they are independent, or in many real applications we assume. Okay. Based on our understanding of the field, of the physics, of the mechanics of the system, we often assume that they are independent, and then we are allowed to assume that this thing is 0, this will hold, this will hold, this will hold, right? But either you assume this or you prove it. This comes with the package. If you prove independence or you assume independence, uncorrelatedness comes as part of that package. But if you assume uncorrelated or you find it to be uncorrelated, independence does not come in the package. Okay, so that was another good or important result we saw. What was the third thing related to?
Correlation is weaker than dependence.
Yeah, that's the same thing. Yeah, independence and that. So what else?
Does not imply causation.
Yes, that's the third important lesson I want you to take away from our discussions last time. Correlation does not imply causation. Yeah, so you remember that two random variables have high covariance or correlation. They could be, that could be happening because of just coincidence. That could actually be that they are correlated, so one is causing the other. Actually, if they are correlated, that means they are correlated. So one could be causing the other. Yeah. Third one could be there is an external factor causing both. Yeah, we saw that two students getting similar marks, when one gets high the other gets high, when one gets low the other gets low. Yeah, could be coincidence. In each case, if you solve their covariance formula, the covariance will come out high. Yeah, but interpreting the covariance, this is what we are coming in. As a practitioner or someone who wants to use this result, you should always be mindful not to jump to causation that they are cheating.
Yes.
Yes, Could be coincidence, could be cheating, or as you said, uh, some assignments might be very hard and others might be very easy. So then this is an external factor.
तो सर इनको डिटेक्ट एनालाइज कैसे किया जाएगा which किसका वेटेज ज़्यादा है हमारे पास, उसके लिए भी हमें इंफॉर्मेशन चाहिए होगी.
Definitely. Once you recognize that, okay, I have this limitation, then you need to create some sort of experiment, control, or include more information in the process, right? For example, for copying, you may have to find that, let's say, are they using very similar steps? You know, sometimes it's very easy. I have received assignments where student A wrote his reg number, and then student B, and he wrote his reg number and the rest of the assignment is copied. So this was additional information that something was going wrong. Yeah, so it can happen. Then you need to include more information. The important thing is to know the limitations of what you are working with, because you know, if you don't know those limitations, what can happen? You can make wrong claims, right? You can end up designing based on wrong assumptions. Yeah, so you have to first ensure through different tests additional information that it is. In some cases, in many applications, it will not matter to you which one it is. Okay, in most mechanical systems, it may not even matter to you which one. As long as there is correlation, you try to use that information to predict the behavior of one variable by observing the other. See if there is high correlation. Let's say we have two guys here in who are mostly seen together in the campus. Let's say two friends, yeah, mostly seen together. So now if one of them is, let's say, not in the lecture, then the chances that the other is also not in the lecture would be high. So by having covariances or correlations, what we often try to do is either predict or design based on observing one thing and deciding the other. Yeah, so in those cases, it doesn't really matter to me why they are together all the time. Yeah, एक दूसरे डर के साथ है क्या है? We don't know. Yeah, I don't care, as long as I can predict and design for that. Yeah, so that was one thing. Lastly, I had already mentioned the relation between covariance and correlation. What was it?
Correlation always between -1 and 1. 1 means highly correlated and -1.
Yeah, but you guys need to learn to say the crux of things.
Normalization.
Yes. Okay. Yes. Make those notes. Crux. Story नहीं. Why? इससे ज़्यादा there is no more efficient learning than this. Okay. Write the details separately. But the crux should be like जो बैनर पे नहीं बड़ा सा लिखा होता. या अगर बैनर पे आप लिख दें 50 लाइनें बड़ी बड़ी, कौन पढ़ेगा, right? It has to be the main line there. बाकी फिर वो मिन जानिब असलम शकील जो लिखना ले right? बड़ा सा लिखा हो जी, वो खुशामदीद और मिन जानिब भी बड़ा सा. If you write all of that, it's just as confusing. Focus on that. So it's a normalized version of covariance. से ज़्यादा simple और क्या होगा, right? You should know, of course. Then where is it normalized to? Of course, it's -1 to 1. And I told you the benefit of that. Basically, it takes away the individual effect. Yes? Yeah. So it kind of tells you, you can easily judge if this is high or low. Believe me, a system could have a very, let's say there could be two X and Y that have covariance 1000, let's say, okay? And their correlation turns out to be just 0.1. And there could be another system that has, let's say, Z and W that has covariance 100, and their correlation may turn out to be 0.9, very high. Okay, what's going on? Basically, these random variables operate on large values. They are talking about distance between cities. Yeah, this might be talking about distance within the institute. So does that mean this is less correlated? No. So within covariance there is something missing. How do you judge, is this value high or low? जैसे मैंने example दी थी marks की, student gets 1000 marks, good student or bad? I don't know,
different
50,000 से लेके कितने में, I don't know, right? So until you normalize it for me, here I know exactly, I know it's highest in negative, in inverse relation is -1. Yeah, so here I can plot from the start -1, 1, very high, very high, yes, medium, medium, very low, very low. I could set or have some guess for it, but and even comparison, these two random variables are much more correlated than compared to these. But here, can you compare? Looks like the opposite, really. Yeah. So who will take away this? The normalization. You see this thing. How much each one of them varies by itself. You divide by that. उसको आप निकाल देते हैं अंदर से. Yeah. You take that out of covariance, and you get correlation. Okay, clear? So this was so far repetition. As I said, now we are moving into random processes, our journey into random processes. So that's our next module now. Into darkness. Do you know what is into darkness? सुना है? Star Trek देखिए कभी? Movie, serial now? What are you, Star Wars fans or some other fan? Right. Anyway, it's reference to Star Trek. So into random processes finally. Yeah. So now we are going to random processes, and for that. I will start with, of course, I've already mentioned some aspects, but I will start by first generalizing this thing. We went from one random variable to two, variance to covariance. Now we want to go two to many. As soon as you're in many, you are in random processes, one way or the other. Yeah. So let's see. What do the concepts of mean, variance, covariance look like in many random variables? Yeah. So from two to many, let's see. Let's say there are, just to get things started, let's say there are x1, x2, x3, xn random variables, right? With each with mean mu1, variance sigma 1 square, and so on. Yeah. Mean mu2, sigma mu2, sigma 2 square, so on. Right. Then let's say there is a sum of n random variables. Okay. That is summation xi, I is 1 to n. Okay. Clear?
Yes.
What's the mean of this sum? This sum is based on, it's a sum of values of a random process. They could say these are values in a random process. There are many random variables. So what's the mean of this sum?
Will produce a ideal random, another random variable.
Are you sure? So what we're looking for is E of Sn. What's your thought? You already know their means, yeah? So then, what's the mean of this?
Summation EXI.
Summation?
EXI.
Yeah. So remember, expectation was a linear
Yes,
operator.
Yes.
It doesn't require anything else. It doesn't say it's independent, not independent, doesn't matter.
Yeah.
So it's basically I is 1 to n E of x I. What is that? So we know these, yeah, I is 1 to n mu I. Yes. So the mean of the sum is the sum of the means. Yeah. Okay. So more interesting. What is the variance of Sn? Yes.
Expectation of
you've already done this for variance of x plus y. Remember ax plus by, if I take them one and one, it turned out to be, what was it? In this case, sorry, variance of x and y was a square vx, so we'll just leave it vx because a is 1 now, b square vy plus 2ab, ab is 1 1, covariance of x y. If you try it for a few more, you will see the pattern. So I'm just going to write the final formula here, but it's not magical. It comes from this understanding. Just make it for 3 and see the pattern and you understand. So I is 1 to n, what? V of xi, which I could also write sigma I squares. Yeah. Plus, this is the new bit. Yes. 2 times summation covariance of xi yj, xj with I less than j. Okay, so what are we doing here? This will do what? Pairs. So there are, let's say if there are 6 random variables, it will do x1 with x2, x1 with x3, all the pairs you can make. Why I less than j?
Because 3 to अगर x3 to x1 लेंगे x1 to x3 लेंगे will same.
To not repeat the pairs. That's already here, right? This thing is included. So we don't want to repeat the pairs. So we don't want covariance x1 x3 and covariance x3 x1 is the same thing. In that sense, it's not different. Yeah. So we don't want to repeat that. So this is what it is. So the variance of the sum of random variables is what? It's the sum of their variances plus these additional covariances term, we will call it pairwise covariance, right, between each 2 pairs. We will come back to this thing later when we define autocovariance function. Okay, we will need to define it later. But for now, I just want you to extend from what we already discussed. Now, what can make this simpler? Can I make some assumption? I haven't made it here, but let's say I were able to make an assumption. What could make this easier?
If this is covariance is 0.
Covariance of what?
Of all random variables that we use here.
All pairs.
Yes.
Yes. So we can say if they are pairwise independent, then these covariances will be 0. Or if we cannot say pairwise independent, if we can say pairwise uncorrelated, which is weaker, we can still get rid of. What we need to get rid of this, either you say they are pairwise independent, which will include their pairwise covariance being 0, or you say they are pairwise uncorrelated at least. Yeah. If that happens, then all these terms will disappear and the variance will look nice as the mean. Some variance of the sum will be sum of the variances. Not generally true. For mean, it's always true. Mean didn't ask for any assumption. Because by its very nature, it's a linear operator. Variance is not a linear operator, so it requires some additional assumptions. With those, if you are able to make in your problem, and we often make for many problems, because it makes analysis so much easier, it gets rid of so many extra terms. Yeah, but don't force it. If they are correlated and you assume that, your results will be way off from the reality. Yeah, so you cannot just drop it. But if you could, so here I am going to say either they are pairwise. I'm not going to write it, but pairwise.
Actually, why are we using this summation to study 2 random variables at a time? Why not multiplication or something else?
Yeah, we will basically we can see most of those. We will come to those, but it's very often that you deal with summations in one form or the other. Also because it's supposedly easier, you could start with that. Yes, but then the pairwise the multiplication. Let's say you wanted to have a product of these. Yeah, what's the mean of the product? What's the variance of the product? Yeah, we could try that, and in some cases it will come. But we want to slowly develop these things, then we will see. So an interesting question for you guys. Let's see if we have quick thinkers here. X is a random variable, K is a deterministic variable or a constant, right? So it's not random. What's the covariance?
Covariance of X.
0.
0. So the covariance of a random variable with
Constant.
a constant or a non-random variable.
Will be 0.
0.
Sir, covariance of X.
Okay. So it will be 0. Oh, yeah. Why would it be 0?
Because it's a constant number. As we saw previously an example where they have a constant number, variance 0.
No, it's one is varying, another is a constant. So that's why.
Yeah.
That's not
Covariance
covariance.
has the degree of linear dependence, or it's also, we said, co-varying, how much they co. K is not going to vary at all. X can go up or down, whatever it wants to do. K is not going to move, right?
So it means that there is a constant line.
Yeah, at least for K. Yeah, so it will lead to horizontal something. Yeah, so the covariance is 0. Right, so what's the covariance of X with X? If K is a constant, that is 0. What's the covariance of X with X?
It is 1 or minus 1. It will be maximum. It is either, it will be 1, I guess.
That's not the covariance of X.
Is correlation lies between -1 and 1. Yeah, but this is covariance, so it has to have something. Can't try it.
Sir, I think there is no covariance or correlation between them. There is a single point.
No, they are not. These are random variables, X and X. X is a random variable, so. You can try in many different ways. Try the formula if you like. कोई निकला?
So let's become variance square.
Variance square? Does it come out to variance of X or no?
Yes, sir.
Right? Try it again at home. Okay? Covariance of X with X is variance of X. Okay? What's the correlation of X with X? That you've already answered. Should be 1.
Correlation.
Yeah, should be 1. You can prove it from the formula also. It's the covariance of X with X divided by square root of V square, because it will appear 2 times X. This will cancel. This is V of X. So V of X by V of X is 1. See the normalizing role of this guy. Do you see it now? It's normalizing. If they are x and y, it normalizes by both their variances. Yeah, right. So in general, I'll write the formula here for, it's a very, these are some useful results. You can prove them easily, check them in the text, try them out yourself, but it's good to then finally note them and use them. Okay, so another very useful relation is that if there is a summation of random variables ai, let's say I is 1 to k, so a1 x1 a2 x2 a up to k, with covariance of a sum of random variables with another sum of random variables, let's say that is b, I'll use j y j, and j is 1 to l. So you can try for some values or try to expand it generally. It turns out to be double summation I is 1 to k, j is 1 to l. Any guesses? ai bj covariance of xi yj. So covariance of sums can be written as sums of covariances. We didn't go up to the variances. Yeah, if you want to stay within covariance, then it is possible to simplify. This formula is very powerful in analytical works. I will show you. It is often helpful to work with covariances rather than variances. So let's see. Let's have an example quickly. Let x equal y minus x minus 3. X is a random variable, y is now a new random variable built on x. Yes, so let's say x has some variance vx, some defined variance vx. I don't give you the value, and then you're asked to find vy. Knowing vx, can you find vy? Okay, try it. What is the variance of this new random variable? Firstly, if you know mean of x, then what is ey, mean of y?
Expectation of y minus expectation of x, expectation 3 आ जाएगा minus यही आ जाएगी sir. Expectation of y is equals to expectation of x minus 3.
Mu x minus 3.
Expectation of y is equals to variance of y is equals to variance of x आ जाएगा हमारे पास.
Sure.
Yes, constant की variance 0 रहती है ना.
Right, constant की variance 0 होती है, लेकिन how I am not doing covariance of, let's say, y with or x with 3, or not doing that. Yeah, so how do you get to that result, variance of y? So what I want to show you here quickly is this thing. Of course you could try to say, okay, variance of y is like, you could go by the basic formula, which would be the expected value of y minus mean y square, one of those formulas. Yeah, but often in such cases it really helps to not go there, okay, and work with covariances. I'll show you. We already saw that the variance of y is covariance of y with y. We saw that? Yes. Use this trick in analytical solutions. We don't go for the quadratic thing. We use this trick. So that means covariance of y minus x minus 3 with x minus 3. Yes, but by this formula you are able to always write covariance as a pairwise thing. Remember, pairwise. Yes. Yeah? So that means you can write covariance of x with x plus covariance of x with minus 3 plus covariance of minus 3 with x and plus covariance of minus 3 with minus 3. Yeah, all these terms are 0, right? Because these don't vary at all, so their means are the same. So this is 0, and this leads to the answer you already gave, but it becomes more rigorous without having to. It doesn't look very useful at this point, but imagine dealing with large, like would be like 100 variables here, random variable, and if you're dealing with that and you try to work with this, it will be a headache. Okay, so analytically often it helps to take the problem or recast variance problems as covariance problems. And this is your key here. Yeah. So you were given a variance problem, but you now recast it as a covariance problem and then make use of this very powerful result, okay, that allows you to do what basically it says. Once you have written it like this covariance is the same as the pairwise covariances, sum of all, and since I didn't put any additional AB, so you don't need them, but if there were, like we could say 5x here, right, something, so then you can include those. Okay, so of course these you have to try out. So what did we do now? The last few minutes we discussed some details about going to covariances and variances of multiple random variables in some ways, yeah, and then we saw some results that will come in very handy when we deal with analytical studies of random processes. Yeah, okay, so again let's start with what is a random process for our case. What is it?
It's a collection of random variables.
So this is kind of a recursive definition. Yes, since we have already established random variables in such detail, we don't need to define it in very general terms. What we can now say is that for us a random process is a collection of random variables. Remember, we went from random event to random variable, yeah, and deterministic event to deterministic random variable, deterministic variable to random variable. Now we are going from random variable to random process, and we briefly saw that, like, the height of next 5 students entering the room, first, second, third, fourth, fifth, if you collect that in some way, this is a random process. Okay, height of the first student who enters the room, height of the second student, height of the third, fourth, fifth, this is a random process. Now we wrote it generally, if you remember. How was it? Remember this one? Omega T was in T, and then we often shorten it to either this thing, we either just write it xt or xt. Okay, but we will come to that later. And we had the underlying assumption of the sample space, omega, sigma field, and probability measured. So we've done that in detail, discussed the, let's say, the underlying concepts between them. Now we have also discussed discrete versus continuous state random variables. Remember? So what was that? Basically, if x takes discrete values, yes, or continuous values, then we say this random variable is either discrete or continuous. Now we have another form of discreteness and continuousness, which is in T. So how do we distinguish between them? So from now on, we will call this, when x, value of x itself takes on discrete number of values, we will call it discrete state random variable. Okay, so based on discrete state, continuous state. And when we say discrete random variable, we will mean this T is discrete or continuous. Okay, so without the state, we are referring to this. Now this is some confusion when we teach at our lower levels, when we don't go into processes, we just call this discrete and continuous. Okay, because for those students for undergrad, we don't even go to, mostly we don't go into T. There we can just say discrete or continuous. What we are actually talking about is discrete state. Now since we are going to handle both situations, we need to be able to uniquely identify. Yes, so just keep that in mind. If T is discrete, we will say it's the collection is discrete random process. If T is continuous, discrete continuous random process. If x can take discrete set of values, it will be a discrete state random process, and so on. Okay. In the digital world, of course, we describe both in time and value. So I will discuss that also. So let's take a few one example of each of these. You can make now, how many combinations can you make?
Different combinations. Its state is discrete and variable is discrete.
चार होंगे ना?
Yes, sir.
Yes. So discrete state, discrete random variable.
Yes, sir.
Discrete state, continuous random variable. Continuous state, discrete random variable, and continuous state, continuous random variable. So let's just get a feel for what does that really mean. Yeah. Each one of them, what could it mean? How could it look like? Let's say I take the temperature in the room over a day. Okay, I measure the temperature in a room over a day. So now, assuming that we don't bother with digital equipment and that thing, temperature by itself, is it continuous or discrete?
Continuous.
Continuous, right? What about time?
It's also continuous.
Continuous, yeah. Okay, we will, mostly when we sample, we will have to discretize, but in reality, or in its very nature, it is continuous. You could make the sampling as high as you like to get close to the continuous state. So temperature in a room, this is temperature. How is the temperature of this room varying? Yeah, over time in a day. Yeah. So what's going on? State is continuous. Yes. The progression of the process or the independent variable is continuous. So this is what? Continuous state, continuous random process. Yeah. Okay. Let's see another example.
सर टेम्परेचर को इंसान हम डिस्क्रीट भी तो ले सकते हैं, 26, 27.
You can, yeah. But if you discretize it, which we will do, of course, yeah. But just for understanding what we mean by something that can have a continuous state, the values allowed are not by their very nature are not limited. Your sensors may be limited, which usually are, yes. But the state itself is not limited, yeah. But yeah, the modern digital world definitely works with discrete, not only in this domain, here also it works with discrete. That is what we call digital. You know what's the difference between digital and, let's say, discrete? Discrete usually talks about just one of them. If you discretize both, we call it digital. Okay, so we will see that. If we wanted to make this a, let's say, continuous state, discrete time kind of random variable, or continuous state, discrete random, what could be a change we could do? There are many ways. I'll mention one. Let's say temperature of people in a room taken at 2 p.m. Okay, so now temperature of people in a room taken at 2 p.m. Let's say there are 4 people in this room. So first person's temperature, something here, second person's temperature, something here, third person temperature, yeah, fourth person's temperature, yeah. Now, which side have we discretized? Temperature itself is still, by its nature, is continuous. So they could have had any value here, yeah. But here, by the nature of your experiment or setup, you have made this discrete. Ab 1.5 banda to nahi hota na, right? So some Kashmiri families, I'm also from that, so I can joke about it. Yeah. So 1, 2, 3, 4, first person, second person. By the very nature, now what is this? Continuous state, discrete random process. Whatever you get now is a continuous state, discrete random process. Okay, now let's think of something else. Discrete state, discrete time, or discrete state, discrete random process. Yeah. So can you think of an example? Let's say stick to the room and people and
How
everything.
much mobiles are 4%?
Yes, good. Actually, that's what I have written here. Number of mobiles next 5 students entering have. Okay, so let's say the five students who enter. Now, x-axis is the student. First student, second student, third student, fourth, fifth. Discrete. Number of mobiles they have, discrete. Yeah. So you plot it like this. Yeah. What's the difference between this one and this one?
This is a continuous step.
The y-axis was continuous.
Continuous,
Yeah. So here y is also
Discrete.
discrete. So mobiles and people. Here people and temperature. So it may not look like from the plot itself, but by the grading here, if you limit it to some fixed values, it becomes discrete. Only this is called digital. Okay. None of the others. Sometimes students think this is digital. If you just discretize over time, digital in its very basic definition means that it is discretized in both. And the world we are living in now is digital. We work with this actually. Okay. So anyway, so what's this then? Discrete state, discrete random process. We could put here time also, continuous state, continuous. But I tried to avoid time because x-axis doesn't have to be time. We say time, but here it's not time. So I tried to avoid that. But discrete state, discrete random process. The fourth one is interesting. What would that be? क्या रहेगा?
Discrete state, continuous.
Continuous random.
ये कोई बना के दिखाया मुझे. क्या था? Discrete state, continuous random process. Yeah. So what does that mean now?
Binomial trials sequence. Binomial trials sequence.
Binomial. So how would you could describe some experiment on that? Let's see. Find some space here. So I think we'll stop after that.
फॉर एग्जांपल क्रिकेट मैच जब हमारे पास चल रहा होता है तो उसमें नीचे आवर्स लिखे होते हैं 2 4 6 8 मगर जहाँ पर विकेट्स आती हैं वो पॉइंट अलग ही होता है. तो स्ट्रेट कंटिन्यूस हो गई और वाई एक्सिस हमारा डिस्क्रीट हो गया.
Wickets.
वाई एक्सिस पर शो होंगी और आवर्स नीचे शो होंगे.
Yeah, but wickets themselves, can they be like continuous? You can have 1 wicket, 2 wicket, 3 wicket.
सर फॉर एग्जांपल अगर 3 आउट हुए तो हमारे पास 3 पॉइंट्स आएंगे, वो डिस्क्रीट हो गए. वाई एक्सिस को हमने डिस्क्रीट करना है और एक्स एक्सिस को कंटिन्यूस करना है. तो टोटल 20 ओवर्स जो चल रहे हैं वो कंटिन्यूस हो गए और जो विकेट्स आ रही हैं वाई एक्सिस पर वो डिस्क्रीट हो गए.
So in some we can say हमारा mobile status जो होता है, so we could say 500 people on your mobile. So in what time, in time T1 and T2 we can see how much people can see our status. So that could be the people
Between time 1 and
between 1 hour you could say between.
Yeah.
Then for one, because
Yeah,
time
yeah.
is continuous, so we can say there are 500 people are there, so we can describe that 2 people are there, 3 people.
So you
are there.
define intervals,
Yeah.
and in that this.
Interval, how much people can see our status.
Yeah, good. So I have another one here. Let's say there is a voltage source, power source, that jumps randomly between 3 voltage levels. Okay. So there is a voltage source. It is going to give us voltage output. This is time, and it can jump randomly between, let's say, alpha 10 volts, 15 volts, 20 volts. Yeah. So it is giving some voltage. Now it decides to jump, but by the way it's designed, it can only take one of these 3 states. Where do you want to jump? When do you want it to jump? And where do you want it to jump? Let's say, just tell me, should it jump? Maybe, let's say random. So jumps here, jumps back, quickly jumps back, jumps. Yeah, if you draw this out, there will be many realizations different. But notice over here it is continuous in the sense that we didn't limit the time axis onto fixed number of values. No values was disallowed. Yeah, it's continuous. But by its very design, it can only produce three voltages: alpha, beta, and gamma. So here it's discretized. Yeah, actually we will see this when we come to random walks, some Markov chains. We will come back to this. Okay, not just voltage. It will be something more general, but we will see it inshallah. So today we started a bit late, so I think I'll stop here. Next time we continue our journey into random processes. Yes, by we have tried to generalize covariance for some cases, try to see some useful formulas for covariance. They will come in handy when we work with random process. And then we have established that once you go into random process, t also becomes important, the time. And then you have to include another thing here, which is talking about the time index. Is that continuous or not? For a random variable alone, it's enough to say if it is discrete state or continuous state, which we just say discrete or continuous. But for a random process, it can be discrete state, continuous state, and then in time it can be discrete or continuous. For a random variable itself, a single variable, the concept of DC doesn't really mean anything. Okay, it's not evolving, or like there's no time index there. Yeah, as soon as you bring in a time index or another index along the x-axis, which could be people also, you turn it into a process, and then you have to qualify it in both. Yeah, so just to give you a general idea what each of these may look like. Yes, so next time we do this similar thing for distributions. We go from two to many.
Yes.
And you know what it will lead us to? It will lead us to distribution families. A random process has the distribution family associated with it. Okay, so we will see what is a family. Okay, so it gets pretty complicated. Lots of writing there. Yeah, but we will just develop the concept, and then we will do that. We will then go for moments from random variable to random process. Most of the things that we have learned so far, we will generalize those to random process case, and then we will see, because for single random variable we have seen first moment was mean. Yes, but for random process, is it just one value or is it a series of values? Yeah, so you will learn the concept of moment functions, okay, or mean value functions instead of just mean value. So we will see that next time.
Okay, so I have one question. It's two different